real image, virtual image, and the mirror formula and linear magnification. So first we have to discuss about what is a real image and what is virtual image. So real image, suppose this is the point from which the ray of light comes, and actually the ray of light, after emanating from the point, they actually converge at a point after reflection or refraction through the lens, and that image is known as the real image. And when the rays, after emanating from the object, they actually do not converge, but they appears to diverge from a point. That image is known as the virtual image. So first we have to draw the diagram, then explanation. So first we have to draw it for the concave mirror. Concave mirror. This side is the reflecting surface and this side is the non-reflecting or polished surface, and this is the principal axis. This is the pole P, and let two ray of light that comes from infinity. That's why they will be parallel to the principal axis. And let this is the focus, and in the previous class we had already derived the relation between the focal length and the center of curvature, that is the focal length, that is half of radius of curvature, and let this is the center of curvature. So this distance is r and this distance is f. The relation is f is equals to r divided by 2. The focal length, that is equals to half of radius of curvature. So the ray of light that comes from infinity will be parallel to the principal axis, and after reflection through the concave mirror, the ray of light will be passed through the focus. So this is the path of the reflected ray, and another ray which is also parallel to the principal axis, after reflection it will be passed through the focus. So here the ray of light, they actually converge at the focus. That's why we can say the concave mirror, that is converging mirror. Here converging, because after reflection through the mirror, the ray of light, they actually meet at the point F or converge at the point F. That's why we can say the concave mirror, that is converging in nature. And next, the convex mirror. In convex mirror, this side is the reflecting surface and this side is the polished surface. This is convex mirror, and let this is the principal axis and this is the pole. Again, the ray of light that comes from infinity, so they will be parallel to the principal axis. This is the another ray that will be parallel to the principal axis, and here the ray of light, they will be diverge like this. After reflection, they will be diverge like this. And here, if you extend them in that direction, that means in this direction, they will be meet at this point. So this point is the focus. That's why here you can see the ray of light, they actually do not converge, but they appears to be diverge from a point. So that's why we can say the convex mirror that is diverging. Because after reflection, the ray of light, they appears to diverge from a point. So we can say the convex mirror that is diverging in nature, and the concave mirror that is converging in nature. So this is about reflection, and comes to refraction. This is the convex lens, and this is the principal axis, and the two ray of here, this is one convex surface, and this is the another convex surface. For this convex surface, so this is the focus, and for the second convex surface, this is the focus. And here, let the two ray of light that comes from infinity, so they will be parallel to the principal axis, and after refraction through the convex lens, they will be passed through the focus. So here we can say the convex lens that is converging in nature, convex lens that is converging. That means after refraction through the lens, the ray of light, they actually converge at the point F. So we can say the convex lens that is converging in nature. Now comes to concave lens. This is the principal axis, and again two ray of light, they comes from infinity, so they are parallel to the principal axis, and after refraction through the concave lens, they will be moved in this way. So actually they diverge, and when you extend them in that direction, they appears to meet at a point. Let this point is F, focus. So that's why we can say the concave lens that is diverging in nature, diverging. Clear? Concave mirror that is converging in nature, but concave lens that is diverging in nature, and the convex mirror that is diverging in nature, but the convex lens that is converging in nature. So the definition of real image: the rays after emanating from a point, they actually converge they actually converge in these two cases. They actually converge at a point after reflection or refraction, and that point is known as the real image of the object. Then comes to virtual image. The rays after emanating from a point, they actually do not converge. Here they actually do not converge, actually they diverge, but they appears to diverge from a point. They appears to diverge from this point, and this point is known as the virtual image of the object. Clear? This is about the real image and virtual image. And then we have to move for mirror formula. Next is the mirror formula. Next is the mirror formula. Remember, the mirror formula is 1 divided by f, that is equals to 1 divided by v plus 1 divided by u, where f, that is the focal length, v is the image distance, and u is the object distance. So we can say mirror formula, that is the relation between the focal length, the image distance, and the object distance. Clear? So before mirror formula, you have to know some rules about the formation of image in mirror. So some rules you have to remember. The rules are that this is the mirror, this is the concave mirror, and this is the principal axis, this is the pole, this is the principal axis. The rules are: when the object is situated at infinity, the ray of light, they will be parallel to the principal axis. That means the ray of light that comes from infinity, they will be parallel to the principal axis, and as this is a mirror, reflection will be there. So the ray of light that comes parallel to the principal axis, after reflection through the mirror, they will be passed through the focus. So the ray of light, they will pass through this point, and this point will be the focus. This is point number 1. The ray of light, they moves parallel to the principal axis. After reflection through the mirror, they will pass through the focus. Point number 2. The ray of light, they pass through the focus. This is the ray of light which pass through the focus. Let the light ray reach here, then as this is a mirror, reflection will be there. So after reflection, it will move parallel to the principal axis. Clear? The ray of light which pass through the focus after reflection by the mirror, it will move parallel to the principal axis. Point number 3. If this is the focus, then we know the relation between the focal length and the radius of curvature. F is equals to R divided by 2. If this is the focus, then this will be the center of curvature. And rule 3, that is the ray of light which pass through the center of curvature will move undeviated. If the ray of light, let the ray of light will pass through the center, then this is the incident ray. Then after reflection, as this is a mirror, reflection will be there, and after reflection, it will follow the same path. That means the ray of light which pass through the center after reflection by the mirror, it will follow the same path. There is no change in its path for the ray of light which pass through the center. Then rule number 4. The ray of light, suppose this is a ray of light which incident at the pole, then it will be reflected. Let this is the angle of incidence I. So it will follow the law of reflection. That means it if this is the reflected ray after reflection, then this angle will be equals to R, and according to the law of reflection, I is equals to R. This is the rule number 4. That means the ray of light which incident at the pole, it will be reflected according to the law of reflection. That means the angle of incidence will be equal to the angle of reflection. You have to remember some rules, and always you have to take small aperture. Actually, this is the spherical surface or the curved surface, and if you take a small aperture from here, it will be a straight line. Always in the optics, ray optics, you have to choose small aperture. Clear? So you have to remember these rules. So next we have to move mirror formula, that is 1 divided by f, that is equals to 1 divided by v plus 1 divided by u. That means it is a relation between the focal length, image distance and the object distance. So first we have to draw the ray diagram. In optics, the ray diagram is first. So first we have to draw the ray diagram. That this is the concave mirror and this is the principal axis. Let this is focus, this is center of curvature, and let the object is situated beyond the center of curvature, and let a ray of light that moves parallel to the principal axis, and according to the laws which we have discussed now, after reflection the ray of light will pass through the focus, and let this is the path of the ray. And another rule is the ray of light which pass through the center, it will move undeviated. And the another rule is the ray of light and this is the pole. The ray of light which incident at the pole should follow the law of reflection. So the two rays, they meet at this point, so the image will fall here. And the another rule is the ray of light which pass through the focus, after reflection it will move parallel to the principal axis, so all the rays they meet at this point. And if AB is the object, then A dash B dash will be the image after reflection. So here we have to derive this formula, 1 divided by F, that is equals to 1 divided by V plus 1 divided by U. So this is for concave mirror. And here let you have to draw a perpendicular, let this is M, let this is E, and this is F. And here always you have to choose the aperture is small. And let here you can see the two triangles A dash B dash F. In the triangle A dash B dash F and triangle E M F. Here you can see this angle and this angle, these two are the opposite angles, so they are equal in magnitude. And here this is the perpendicular and here this is the perpendicular, so these two angles are equal. That's why we can say the remaining angle, this angle will be equals to this angle. That's why we can say triangle A dash B dash F and triangle EMF are similar. Triangle A dash B dash F is similar with triangle EMF. That's why we can say the ratio of the sides will be equal. And here let the ratio of the sides A dash B dash, that implies A dash B dash divided by, for EMF the side is EM that is equals to B dash F divided by MF, and here you can see this ray of light, the green, that is parallel to the principal axis. That's why we can say the height AB, that is equals to EM. Clear? So here in place of EM we can write AB. That implies A dash B dash divided by AB, that is equals to B dash F divided by MF. That this is equation number 1. And again the triangle, another two triangle are A dash P dash P. In triangle A dash B dash P and triangle ABP and triangle AVP. In the two triangle, this angle is equals to this angle, because this ray of light will follow the law of reflection. That's why these two angles are equal. And again this angle and this angle are equal, right angle. That's why we can say the remaining angle, this angle will be equals to this angle, and we can say triangle A dash B dash P is similar to triangle AVP. As the two triangles are similar, we can say the ratio of the sides will be equal. That implies the ratio of the sides, that is A dash B dash divided by AB will be equals to B dash P divided by BP. Here this is equation number 2. And here in equation number 1 and 2, if you compare both the equation, here the left hand side the terms are equal. That's why you can say these two terms are equal. So you can write from equation 1 and 2, B dash P divided by BP, that is equals to B dash F divided by MF. Clear? B dash P. What is B dash P? As A dash B dash is the image form, so we can say B dash P, that is the image distance, and BP, that is the object distance, and B dash F is the distance between the image and the focus. That is nothing. So we have to change it in terms of U, V and F. Always you have to take, for ray optics the aperture should be small. For small aperture, when you take the small aperture for a small person, the spherical surface of the small person will be a straight line, and when you choose a small aperture, then you can say the point M and P, they will be at a same point, or you can say M coincide with P. Then in place of M we can write P. So here in place of M we can write P. That implies B dash P divided by BP, that will be equals to B dash F divided by MF, that is PF, for smaller aperture. For smaller aperture. Clear? Then here B dash P, that is the image distance by using the sign convention. B dash, that is situated left to the pole, that's why we can say it is negative. Image distance is V, and by using the sign convention it is minus V. Then BP, that is the object distance BP, again by using the sign convention it will be minus U. And B dash F, so we can convert B dash F in terms of focal length and image distance, and we can write here the equation is B dash P divided by BP, that is equals to B dash F divided by PF. So B dash F, that implies B dash P divided by BP. We can write B dash F as B dash P, this distance minus this distance, that is equals to B dash P minus FP, PF divided by PF. So B dash P is the image distance and PF that is the focal length, and again by using sign convention it is minus F. Now put this value here, that implies B dash P, that is minus V divided by PP, that is minus U, will be equals to B dash P, that is minus V, and PF, that is the focal length, minus this is minus. So you can take a minus common, so this will be V minus F divided by PF, that is minus F. Clear? So minus cancel, so this will be V divided by U, that is equals to V minus F divided by F. Now cross multiplication, multiply V with F, so this is VF will be equals to multiply U with VF, so this is UV minus UF. So you find this equation. Now you have to divide both the sides by a common term, that is now divide by with UVF, the common term UVF. So this will be VF divided by UVF, that is equals to UV divided by UVF minus UF divided by UVF. So VF cancel, UV cancel, UF cancel. So the remaining terms are 1 divided by U, that is equals to 1 divided by F minus 1 divided by V. So by taking V into this side, you can write 1 divided by F, that is equals to 1 divided by V plus 1 divided by U, and this is the final formula. This formula is called mirror formula. You have to remember this formula, and in the question what is given, you have to put the value according to the sign convention. When the given thing is situated left to the pole, they will be negative, and right to the pole, they will be positive. According to sign convention, you have to use in the formula. And this is the mirror formula. You have to remember the mirror formula is 1 divided by f, that is equals to 1 divided by v plus 1 divided by u. That is the relation between the focal length, the image distance, and the object distance. Here, you have to remember important one. And then linear magnification. So what is magnification? So if you compare the image to the object, and where the size of the image is more and the size of the object is small, for that case when the size of the image is more and the size of the object, or the height of the image is more and the height of the object is small, you can say the image is magnified. And when the height of the image is small and the height of the object is more, you can say the image is diminished. So the formula of linear magnification, the formula of linear magnification M, that is height of image to the height of object. Here, height of image to the height of object. And again, we can derive the magnification in terms of object distance and image distance. And again, in the triangle A dash B dash P, in terms of object distance U and image distance V. The image distance is V. So in triangle A dash B dash P, triangle A dash B dash P, which we have already discussed, the triangle A dash B dash P is similar with the triangle ABP. Is similar with the triangle ABP. That's why we can take the ratio of the sides and they will be equal. And here we can write the ratio of the sides A dash B dash divided by AB will be equals to B dash P divided by BP. So what is A dash B dash? A dash B dash, height of the image, and let height of the image HI and height of the object is HO, and A dash B dash, that is the height of the image. So that implies HI AV, that is the height of the object, HO will be equals to B dash P, B dash P, that is the image distance. And if you use the sign convention, this will be minus B, and BP, that is the object distance, and if you use the sign convention, this will be minus U. So minus minus cancel, that implies HI divided by HO will be equals to V divided by U, that is the magnification or linear magnification. Clear? You have to remember the formula of linear magnification, that is the height of the image to the height of the object, and in terms of image distance and object distance, the magnification is the image distance, the ratio of image distance to the object distance. And you have to remember, when m is positive, here m is negative, and when m is negative, the image form is real. That means the image is situated below the principal axis, that's why m will be negative by using the sign convention. And we take m is positive means the image will be situated above the principal axis, that means with the same side of the object. That's why we can say the image is virtual. And second, when m is negative, when m is negative, it will be real and inverted. Real and inverted. M is greater than 1. When m is greater than 1, we can say it is magnified. And when m is less than 1, it is diminished. And when m is positive, that is inverted. Sorry, this is erect and virtual. Erect and virtual. So this is about the linear magnification. The formula is height of image to the height of object, or image distance to the object distance. And when m is greater than 1, more than 1, when m is equals to 1, we can say the height of the image is equals to height of object, or the image distance that is equal to the object distance. And m is greater than 1 means the height of the image is more than the height of the object. That means we can say the image is magnified. Clear? And m is less than 1 means diminished. The size of the image decreases with compared to the object. And m is positive, that is the image is formed above the principal axis, that's why it will be virtual and erect. And m is negative means the final image that forms below the principal axis, that's why it will be real and inverted. This is the case.